Hi, welcome everyone. Thank you for joining us live. And for those of you joining us in the future, welcome to you as well. I'm going to tell you a little bit about the Country Bookshop and then we will start our chat with Marcus about blueprints. The Country Bookshop is located in Southern Pines, North Carolina, and it is an honor to be a part of our community. Community is crucial to what we do at the Country Bookshop. We exist because you choose to shop with us, because you choose to have conversations with us and allow us to provide a space for you to wander through and discover new ideas and books on our creaky floors um, and a place to bring your kids on a rainy day or send your in-laws when they're visiting for too long. Thank you for accepting our invitation to join us and meet authors in the store or in town, or to engage in conversations like today with authors from afar, like Marcus, that brings the conversation close to encourage you to read the book. Every time you engage with us, specifically when you buy a book from us, even if that's online or over Instagram or Facebook or through our website, or buy an audiobook from us through Libro FM, you allow us to do this and more. One of my favorite things about the bookshop is being able to bring authors into schools in rural North Carolina and just watch kids as they light up from interacting with the author from all over who've come into rural North Carolina, deep rural North Carolina, and tell them secrets about story and science. And then the kids go home with an autographed book of their own. And I just want to thank you not only for showing up today and listening, but for making that possible. The bookshop was founded in 1953, and in 2010, when we were in danger of closing our doors, our local newspaper, The Pilot, bought the bookshop. And we love being a part of local community journalism, where reporters are showing up at meetings and reflecting our community and providing spaces for things like letters to the editor. So thank you for showing up. Uh, Marcus, how specifically do I pronounce your last name?
Yes, everyone always gets a little bit confused by it because it's clearly got a kind of French origin. So, when I go to Paris and give talks, it's du Sautoy, but actually we say du Sautoy. And I used to think it had been anglicized, but when I was talking to a professor of French in my university in Oxford, he said, "No, when did you come to England?" And I said 1745 was the family. And he said, "You're pronouncing it in pre-revolutionary French. So it's old French style. So de Sautoy is actually Ancien Régime."
De Sautoy. I do love how the order it gets, the ease, it's like sounded out easier almost.
Yeah,
Well,
exactly.
Marcus du Sautoy is the professor for public understanding of science and the professor of mathematics at the University of Oxford. He's a fellow of the New College and of the Royal Society, presented on numerous radio and TV series, including the BBC Story of Math, and is a playwright who lives in London. I want to read you a list of some of his books: The Music of Prime, Around the World in 80 Games, Thinking Better, The Art of the Shortcut in Math and Life, Number Mysteries, The Great Unknown, The Creativity Code, Art and Innovation in the Age of AI, and Blueprints, How Mathematics Shapes Creativity, where he explores mathematics, art, and nature and tells us that they're the equal partners in our equilateral triangle of ideas. So now we get to talk.
Wonderful. Well, thank you so much for having me in your bookshop virtually. But I so agree with you about the importance of bookshops, actually, in your introduction, because I would say, one of the reasons that I chose the mathematical path was a teacher recommended a couple of books, and I went to my local bookshop in Oxford. It's called Blackwell's, and it was like discovering this kind of amazing Aladdin's cave of ideas, and the books I took away that kind of Saturday morning really just set me on the course for where I am today. So, bookshops are such an important, and libraries as well, of course, such important places to kind of ignite the passion, which could be, your life's work.
Well, it's interesting because I feel like having read this, I feel like we get to go on this journey with you from those initial books. Like you talk about the book of math, of course I'm going to mess it up, but the mathematics, the one with the A.C. Snow introduction about the two cultures,
Yes.
That
Yeah, it's called yeah, it's called A Mathematician's Apology. It's a really small book, but it's by a Cambridge mathematician, sort of early 20th century, really about what it means to be a mathematician. And that was one of the books that my teacher, when I was about 12 or 13, recommended to me to kind of light this fire of mathematics inside me. And it was there that I first read about this connection between mathematics and creativity. Because I think, a lot of people uh, probably think that, the creative arts and mathematics are sort of almost polar opposites. One creative arts is about your emotions, expressing your inner world, and mathematics seems to be about cold logic and very inhumane. But actually, that book talks about the mathematician G.H. Hardy talks about mathematics as a creative art. He compares it to painting or poetry. And for me, I was like at school, I was sort of beginning to be just I love the world of science. I was first, it's the first time I've been in a lab doing experiments. But I also was enjoying the arts. I was starting to play the trumpet, doing theatre, and I sort of was frustrated by our education system, which seemed to want us to choose between these, and I wanted to do both. And I think that book that I read, Mathematician's Apology, created this bridge that there's creativity in mathematics, but it's also, it's the language of science. So it was a very important book, and I would say was the seed for growing this book, Blueprints, which is all about the way that mathematics gets used by creative artists, but also how mathematics itself is about storytelling.
I kind of love listening to you because now we exist in a world where kids are going to discover this book, so which is
Oh,
kind of the continuation in the circle. But I want to start by asking you, about this translating, because taking these blueprints, these mathematical blueprints from one language into another, a medium into another, a time into another, as you were talking about that book doing for you. And I was wondering if you could talk a little bit about how you understand translation, a little bit.
oh, that's so interesting because, in a way, my first idea for structuring this book was to start where people are kind of happy, which is like in the world of music or literature or architecture, and then to sort of reveal the mathematics that's kind of the language that's hiding behind that. But actually, I decided to flip it and kind of be brave and start with the mathematical structures, and then to reveal how. And they're my blueprints. That's the word. Blueprints is my kind of friendly word for mathematical structures. But then to see how, as you say, how they get translated into different art forms. And in a way, it was a way more interesting way to structure the book because, for example, the first blueprint in the book, the first mathematical structure are prime numbers, these indivisible numbers like 7 and 17. And what I was fascinated to see was how they get translated in different ways into different kind of art forms. And I think for me, that was one of the revelations of the way I wrote this book was taking a structure and then to see how differently people use that in their work. Musically, the primes, I start with a story about Olivier Messiaen and how he used them to create a really strange effect in a quartet he wrote. But then in architecture, they're used actually in acoustics for creating concert halls that don't have kind of weird echoes or dead spaces. And then if you move to literature, very interesting example of how Shakespeare uses prime numbers in his writing. So I loved this idea that one idea can be translated into many different ways across different art forms.
Um, I do love, I just to reiterate the Shakespeare, if you could just
Yeah,
mention
I think,
quickly how he used, and I could say just real quick, I loved really being reminded about the pattern and the meter, and then how it switches to prime to signal something that
yeah,
deep.
exactly. So I think it was one of the surprises that I got in the book. Writing this book, it's always fun to write about the things you sort of know about in advance. But I actually got asked by a festival that was celebrating a Shakespeare anniversary. Um, could you do a talk about Shakespeare and maths? And my initial reaction was, gosh, I don't know anything about Shakespeare and maths, because, you think of Shakespeare as a wordsmith, not as somebody interested in numbers. But um, one of the lovely things about being in Oxford, a fellow in Oxford, is we have this collegiate system, which means that we collect together people from many different subjects in each college. So in my college, New College, which of course in a very Oxford way is one of the oldest colleges, I meet at lunchtime people from many different academic disciplines. And one lunch I got to sit next to the English fellow, and he's an expert in Shakespeare. So I was like, oh, here's my chance. So I asked him, look, I've got to do this talk now, Shakespeare and maths, and I don't know what to say. And he said, oh no, Shakespeare has some incredible mathematical ideas running through his work, and one in particular were these indivisible numbers, the primes. So um, many of your viewers probably know, well, Shakespeare writes in iambic pentameter, which is 10 syllables broken up into 5 groups of 2: short, long, short, long, short, long, short, long, short, long. But he doesn't always do that. And as you pointed out, when he wants to disrupt things, he breaks that very even 10 into something like 11 beats, a prime number, which is very crunchy in a way. It's very indivisible. It doesn't quite. And so the most famous line in Shakespeare, to be or not to be, that is the question. It's 11 beats. And, Shakespeare's doing this to wake you up, because you've got to, perhaps you're drifting off with the lovely iambic pentameter in Hamlet. And then suddenly here comes this line, the beginning of one of the most important speeches about the idea of what happens after death. And he uses this 11 to kind of wake you up. And I, actually, in Macbeth, and one of the other famous lines, is this a dagger that I see before me? Shakespeare didn't need that. He could have just said, is this a dagger I see before me? But that creates, again, 11 beats. And so you're kind of jumped out of, and you realize this is important. Now, he has another example of a different prime number, 7, which he uses whenever there is magic afoot in his plays. And of course, he has quite a lot of magic. For example, in Midsummer Night's Dream, Puck has a magic potion that he squeezes into the eyes of the lovers to make them fall in love with the wrong people. And he uses 7 beats again, because this is magic. Churl, upon thine eyes I throw all the charm this plant does. Oh, I think something like that. But it's 7 syllables again. And so Shakespeare's using numbers as a code to indicate important things happening, magic happening. Macbeth again, when shall we three meet again? 7 syllables. So I think it's really fascinating that he was sensitive to number and using the different rhythms that he can make to create these different effects.
Well, I love it. And I do love how you chose to structure the book starting with the math and then directing the discovery, because it allows those of us reading to do it ourselves. And and because we're starting and then we're naturally like looking for the pattern and where we see that. And it was fun for me to explore symmetry, because I realized that is translation. That's like finding the symmetry as the idea moves. But you lead us to play, and throughout the whole book, and getting to see, we were talking about your space earlier, but it's full of play and exploring and being on the lookout. I have a whole list of words that you just use over and over: interested and imagining. And the language you use kind of creates this atmosphere of like play and discovery that kind of surrounds art and mathematics throughout time, because you're dealing with time, and it's just delightful. And I was wondering if you could talk about this theme of exploring boundaries and in play that's kind of present every blueprint as it's discovered.
Yeah.
And specifically, I'm kind of curious if to hear you talk about the kind of mindset that allows that kind of exploration.
I think you picking up on this word play is really important because I do feel that that's what I do as a mathematician. That my best discoveries are through kind of playing around with ideas. But I think in your introduction, you also pointed out that I've written two plays, and now it's interesting that theatre uses this word play, that we are sort of playing on stage. But I think I've worked a lot with different theatre companies over the years, and if you're devising theatre, for example, through improvisation, then improvising is quite tough, because if you just throw a couple of actors on the stage and go, okay, improvise a scene or whatever, they'll clam up. And this is one of the things with, if you're doing anything, if you're writing or composing music or painting, the blank page or the blank stave of music or the blank stage of the theatre can be really terrifying. And it is not conducive to creativity or play. And this is why I think the connection with mathematics in particular is the one of the words which comes up a lot in the book is structure. And I think that when you're playing, one of the important things is to have a kind of safe or interesting structure within which to move. If you do not have structure, then it's almost like, one of the books that you mentioned that I wrote before this book is Around the World in 80 Games. And, games work by having a set of rules. And if the rules are good, it allows you to play the game and you can explore different ways of navigating that game. And I think actually creative artists are often playing a game, that they are setting up some structure, some rules. So, for example, in the case of theatre, you might have a set of rules that the actors have to work within. And then if the rules are clever, then you'll find really interesting magical things emerging out of those constraints. So one of the people I quote in the book is Stravinsky. Stravinsky, the composer, he said, I can only be creative under huge constraints. That if you have no kind of rules or boundaries, then play is really difficult. But if you have some structure that has some freedom within it, then somehow the play will easily emerge from that. And I think that's the same for me as a mathematician. I like the constraints of the kind of logic or the structures that I'm working in, because weirdly they provide me and push me into new ideas that perhaps without them they would never appear. So I think those structures, whenever you talk to any artist, for example, I do a lot of music. Music is one of the big themes in this book. And if you talk to a composer, they will often say the structure is first and the emotions emerge out of that structure. So, I mean, I did an event in New York actually with Philip Glass a few years ago, and he said, the emotion is the secondary thing. I am most interested in exploring some rules and structure, and if they're exciting, then that's why the emotion appears, because you resonate with the excitement of that structure.
When you talk about in your blueprint of randomness, you kind of talk about art and audience participation, and you kind of mention some of the artists, including the audience, some actually not doing it in a total random way, and you mentioned that, but I'm curious about um, this structure. Give me a second to spit this out, but kind of the function of the art taking the viewer or listener or reader to make the choices for themselves and participate in the work and kind of turn it from like a 2D form into a 3D. I guess that would be four-dimensional because they're participating. I'm trying so hard here, Marcus. Um,
Yeah. Well,
but
it's yeah, it's very interesting. You see, um, I think that an undervalued part of the creative process is the listener, the viewer, the visitor, because they are as much part of that creative process. And I think, perhaps that's one difference between mathematics and the creative arts. I'm looking at a lot of kind of overlap and similarity, but one of the big differences, I think, is this word ambiguity, that a piece of art actually enjoys ambiguity such that it isn't forcing the person who's engaging with it in just one direction, and it allows some sort of um, uh, the kind of the reader or the viewer is or the listener is bringing some of their own creativity to a piece of work. I think in particular something like poetry does that in a very big way, because there's often a lot of room for interpretation, and that's the fun thing. Different readers will have different ways of engaging with it. But I think the you mentioned this blueprint of randomness, which is kind of curious because in a way, isn't that a like an anti-blueprint? It seems to be sort of have no structure to it. But strangely, randomness, and this is something that mathematicians have kind of understood, does have its own signature and pattern. But I was kind of curious how, a lot of artists, especially at the beginning of the 20th century, who are trying to kind of break out of the rules of the previous generations, which, like the Dada movement really felt that somehow the structures of the art world had been partly responsible for things like the First World War emerging, that the politics was a result of the rather constrained thinking. And so the Dada movement, which is the one I start the randomness chapter with, they were really interested in using the idea of giving up agency, allowing something to just randomly fall. And in particular, the Dada movement were interested, for example, in cutting up paper, allowing it to fall on the ground, and then seeing what the pattern was that emerged, which wasn't a result of their agency. So, but then that might stimulate you into a new kind of way of thinking. And I think that's the exciting thing. And there are lots of interesting examples where, that randomness is actually given to the reader or the listener as a way of them engaging in a very unique way with the particular art form. So, in particular, B.S. Johnson wrote this rather extraordinary book, The Unfortunates, which is 27 chapters. The first and last chapter are fixed, but the 25 in the middle, basically the reader can choose to read them in any order they want, which means, I mean, that's how many different novels are there are 25 factorial novels, which is way more than there are people on the planet. So that means that there's a unique book for each person on the planet that they can make by using that randomness. And it's not just a gimmick, because B.S. Johnson's book is trying to capture the idea of memory. He's talking about, in the novel, about a friend of his who died, and he goes back to the town where he first met the man, and he has all of these memories flooding back about pubs he went to, or stories they engaged in, or football teams. And so the nature of memory is that it doesn't come in some neat order. You have memories from recently, then very far memories, the memory of when you first met. And so the randomness is a beautiful structure that's used there really to capture the concept of memory. and each person's memory of a particular scenario will be different, which is why each reading of that book is genuinely different for each different reader.
I think it's so interesting because reading your book and also in this thing, this idea of the environments of influence on the output, which is so much of what we're talking about in this randomness, I think. But I'm wondering, you talk about the emergence of like the new geometry in the 19th century, and at the time it all happens at once, but this idea that there is a time for certain ideas, and part of it, you talk about tools, you talk about, waiting for people to figure out, they didn't have the tools to render stuff. And so they were creating geometry with a straight edge and a compass. And then time goes on, and then we figure out something else, and then we can move forward. And right now you're functioning in, today's tools, which are profoundly different. But one of the things that I found really intriguing when you talk about the emergence of the new geometry is that you talk about it as a powerful mathematical metaphor for the way, I'm quoting you, by the way,
Right.
a powerful mathematical metaphor for the way that society needed to question the blueprints it used to frame its current view of itself, which I think is also what you're talking about with Dada. But I'm
Yeah.
wondering if you can talk about like the kind of mathematical metaphors you see it play today, or just, take it where you will.
Yes, I mean, I think that example of the geometries, I think, was really interesting because it sort of that middle of the 19th century, mathematicians suddenly came up with the fact that there are many different geometries and only one will fit our universe. And for example, Dostoevsky uses it in The Brothers Karamazov as the three brothers. One of them is really challenging the idea of religion, questioning whether there is a God, and that he literally talks about the discovery of these new geometries, maybe pushing us to question things like, maybe parallel lines do meet, and maybe there isn't a God. So I think that what is fascinating is seeing the the mathematics and the science of its time influencing the art. I mean, another example is, for example, Salvador Dali, who just loved immersing himself in the science that was emerging in the 20th century, which was really challenging the way we think about our place in the universe. Time is not kind of constant. It can vary according to how you move relative to each other, and he wanted to capture that idea, and the idea of maybe we live in more than three dimensions. And so he has an amazing canvas with Christ being crucified on a four-dimensional cube unwrapped into three dimensions, which has a kind of like cross-like structure to it. But I think that's what's so interesting. For Dali, this idea of a fourth dimension was kind of intriguing. Is that a spiritual dimension? I mean, he was a very spiritual man. So I think it's very interesting to see how these different ideas get reflected in the art. But I think one of the really interesting stories in the book is that sometimes this goes the other way around. That sometimes the drive of wanting to find interesting new structures, aesthetics, discovering new art forms sometimes leads to the discovery of new mathematical and scientific ideas before the mathematicians have discovered them. So, one of the examples is, your viewers might know a very famous sequence of numbers called the Fibonacci numbers, which go 1, 1, 2, 3, 5, 8. And then you might have spotted the pattern. Oh, yeah, you add 5 and 8 together to get 13. 8 plus 13 is 21. These are named after Fibonacci, who was a mathematician and scientist in the 12th, 13th century, because he found them all over the natural world. But I discovered that actually they were discovered several centuries earlier, not by mathematicians or scientists seeing them in nature, but by Indian poets and musicians, because these numbers help you to count the number of rhythms you can make with long and short beats. And we've already heard that Shakespeare used iambic pentameter, which is short, long, short, long, short, long. But what if you wanted to mix that up and do sort of a weird combinations of shorts and longs? And the Indian tabla players were really interested in like trying to create as many interesting rhythms as possible. And they realize these numbers tell you how many rhythms you can make and actually almost give you an algorithm for making those rhythms. So I think it's so fascinating to see it was musicians and poets understanding a fundamental structure before the scientists and mathematicians did. And there are quite a lot of stories like that where artists, you mentioned symmetry, artists were creating all the different ways. I mean, I'm looking at your wonderful tiles in the background. The question about how many different ways you can tile with symmetry. It's the artists of the like in the Alhambra in the 14th to 16th century who are actually exploring what's possible. And it was only at the end of the 19th century that mathematicians came up with the tools to be able to articulate really what was going on in the tiles in the Alhambra. But actually, the artists were already kind of playing that word again around with the tiles and discovering all the different ways that you could sort of create symmetry on a wall.
I love it. Yeah, because to your point of how you answered the question earlier, which I really appreciate, is that uh, creating the structure within which to play. Finding, that this exploration finds the blueprint, which
Yeah.
is your whole point. Um, One of the things, and this was a question you kind of just mentioned it, and I don't mean to put you on the spot because I know you wrote this like 2 or 3 years ago, really, because it's been out in England. And I know it's just been out in the US for a month, but so forgive me if this is too specific. But so you mentioned, and we're an hour away from Duke University, but this researcher, Adrian Bejan, I'm not sure how to pronounce it, but you mentioned briefly his paper about like the human eye and how we better assess information when it's in the golden ratio.
Oh, yes.
Okay, and
Yeah, it's
I
fascinating because the Fibonacci numbers actually are very connected with this other important structure, which is one of the blueprints, which is the golden ratio. And this is a kind of rectangle which has special proportions. So it's a rectangle where if you take the ratio of the long side to the short side, so you take the length of the long side, divide it by the short side, if that is the same as taking the sum of the two sides and dividing it by the long side, we call this a rectangle in the golden ratio. And it's a very aesthetically pleasing rectangle. And you'll find many canvases that artists use to make their work, you'll find that they are in the golden ratio. And the question is, why is this aesthetically pleasing? And part of it is because if you take squares that are in the Fibonacci ratios, like 1 by 1, 1 by 1, 2 by 2, 3 by 3, you can kind of stack them around to build up a rectangle which gets closer and closer to the golden ratio. So it turns out that these Fibonacci numbers help build in a kind of spiral structure a rectangle in the golden ratio. Now, because these Fibonacci numbers are all over the natural world, it means that a lot of structures that grow using these Fibonacci numbers will grow into things which have embedded in them this ratio of the golden ratio. So in a way, what we're probably doing is responding to the fact that when we see something in the golden ratio, it feels literally natural. It's something that we see in nature. So this is uh, one reason that the golden ratio seems so special. But it also seems to be connected with the way that we scan an image. And this is what the research at Duke University is referring to, that when we're I mean, a lot of things go back to our kind of evolutionary process. And when we're assessing, whether as hunters, whether there's anything in the view ahead of us, or if we're being hunted, if we're trying to see whether there's a tiger there, we want to be able to assess very quickly with our eye kind of an area of land. And this piece of research kind of hinted at the fact that the way the eye and the head can assess um, the land in front of you. If you think about it, it's going to be pretty horizontal. It's going to be an area which is a rectangle where you're mostly interested in land going kind of horizontally. So the area that you'll scan will be a rectangle. And again, this kind of idea of the spirals, this is one of the reasons Leonardo loved the golden ratio, because your eye gets naturally drawn to certain places in this landscape and in a canvas. And Leonardo will use this, the way the eye engages with that rectangle, to draw you to certain things in the canvas. You might say, where should you put the most important thing? Some people might say, well, bang in the center. No, but no, Leonardo doesn't do that. So he puts things at interesting places where the spiral of these Fibonacci numbers will take you, and there you'll find interesting things in the Last Supper happening, rather than say slap bang in the middle. So I think the way the eye is engaging it's it's about the way the eye engages with the natural world, which then becomes very powerful when you take it into the artistic world. And actually, you mentioned the kind of blueprint of the equilateral triangle right in your opening, and this is one of the things which is key to the whole book. I would say this blueprint of the book is a triangle where you've got art in one corner, you've got mathematics in the other, but the thing which unifies them is the natural world. That these structures, these blueprints, are very often already there in nature. And you've got symmetry already there in nature, primes, weirdly. I mean, North Carolina, you might have these cicadas, don't you?
Oh
um
yeah.
the
You
prime
talk
number
about them in
cicadas.
Tennessee, but I knew that sound intimately.
Yeah, exactly. Because the East Coast of America has these crazy insects which only appear on a prime number year, and they're using, the primeness to keep them out of sync, probably from a predator. So, what's fascinating in the book is to see that, mathematicians and artists are interested in the same structures, probably because they already are being used by nature, and we're responding with our different languages. Mine's the language of mathematics and equations and geometry and numbers, but a musician is responding to those structures with music, a writer with words, Leonardo with paintings. So, those structures are often already there in nature.
Well, one of the joys when all of y'all watching now or later buy the book from the Country Bookshop is that you start to see these patterns that Marcus has laid out. One that struck me specifically about this scanning is some years ago, for trying to be better at my job, we studied the retail doctor and how we're supposed to lay out the store when you walk in and how customers engage when they walk into a space. And it's exactly what you're talking about.
Yeah,
So
that's so interesting because, yeah, I mean, it is a kind of your visitors are doing a dance through the bookshop, and if you lay it out in one way, you can create uh you know fluid movement and a beautiful dance. But if you do it in another way, you can suddenly box people in, and the creativity to move in the space isn't there. And that's why, choreography is one of the art forms I talk about, and the power of a mathematical idea to create interesting geometry in motion. So, that's what your stage is doing in the bookshop.
well, and what I love is as a part of telling that story, you illustrate how this is translated into the image and creating a geometric alphabet for movement and back and translating the, just in telling that story, you further like fractal it all out. And it's like, here's the translation of it through all these mediums, which is I mean, it's such a treat for the reader what you do. But I did want one thing that this guy from Duke said, and you put it in there, and I'm gonna read the quote because I'm gonna ask you tell me more on it because it made me think of this other stuff. And anyway, to quote you, quoting his paper, animals are wired to feel better and better when they are helped. And so they feel pleasure when they find food or shelter or a mate. This is why he believes that when we associate the idea of the golden ratio with beauty, because anything that helps an animal to navigate its way through the world is going to make it experience gratification. And so I was thinking about how this relates to your book, The Creativity Code, and your conclusions about transformational creativity. Then I was thinking about um, this book called Wanting, which is the power of mimetic desire in everyday life. And his kind of conclusion about the transformation of desire, which is basically the same thing as transformational creativity, but it's basically also just wanting the good for others is what he's talking about. And I'm wondering if how this all fits. Maybe I'm curious more and more, and then I haven't, but about these mathematical, because social structures are creative structures, right?
Yeah.
So I'm wonder I'm just this is where this is the soup of my thinking, and I'm not nothing's I don't have a blueprint yet, Marcus. And
No, I think I mean one of the fascinating things in writing this book, and actually the previous book you mentioned, The Creativity Code, which is my exploration about whether a computer can be creative, and we're starting to see that with generative AI and things. I was very interested in just how we define this idea of creativity, and I think that uh, because creativity, of course, goes beyond just something beautiful. I mean, we associate in that quote, the idea of beauty being about finding somewhere which is, maybe a safe space for us or making us feel good. But I think creativity does something more. And there are two definitions that I used actually in the creativity code. The first one was by Margaret Bowden, a cognitive scientist, which I liked, which is creativity is something which is new. Yeah, that's fine, but has to be surprising and have value, is what she said. So the surprise is about engaging our emotions and making us see the world in a new way. Oh, I didn't realize that. And then, but it shouldn't just be like for shock value's sake. It needs to have some value. It needs to, in the end, perhaps help you in living in the world. But I tell you the definition I really enjoyed. Actually, I've got the book here. It's by Carl Rogers. Carl Rogers, is a psychologist, very influential in psychology, but he had a lovely essay, which is in this book, on about creativity, and he sort of talks about creativity being almost like this tool that our species had developed in order to try and explore this kind of strange thing of our inner world, our emotional world, our consciousness, our subconscious, but also to kind of connect with the consciousness of another being, because that's what we're doing now, and we're using our this is quite a creative process in its own right, a conversation between two people that haven't met, but we're using as our structure this book. But in our way, we're getting to know each other's inner worlds and connecting. It also helps me to reassure myself that you aren't some kind of AI creation, which is kind of some, maybe you're enjoying a cup of tea somewhere and you've got this wonderful avatar. Our creativity is a way of kind of exploring the commonality, the differences. When I create a novel or a poem or a piece of music, I might be actually trying to explore my own inner pain or my ecstasy, and that's a very difficult thing to kind of articulate. And then is your ecstasy anything like mine? Is your pain anything like mine? And so my feeling is this: our creativity is a very important tool for us as a species, not just for that idea in the quotes that you mentioned of feeling in a good place, but actually is our language for kind of solving something which is, one of the big problems in science, which is the hard problem of consciousness. About the trouble is that we're stuck inside our own heads, and it's very hard to imagine what it's like to be you.
Yeah, I recently, and this is before I read your book, but like knowing this this conversation was coming, I gave a talk on creativity and went down the rabbit hole of kind of I'll send it to your publicist to send to you, but like to your point of the audience responding, that constant back and forth response. But it's interesting you talking about your uh, pink book you just held up, that's kind of what I took it in a different direction, but that's what he's exploring. Um, Crazily, we only have like 15 minutes left, but one of the things that I'm really curious about, and I would love for you to talk about in this lens, you just kind of led into it about us being stuck in our heads and trying to get out of our heads. And you start addressing it at the end of the book. But this concept of perfection and beauty, and does perfection, I have it written down, but I'm really curious about about the relationship between perfection and beauty in mathematics, and like the abstract world versus the physicalized world. And you mentioned, are you an avatar? We live in this world where perfection and where we're engaging with it in different ways, but does it exist in the natural world? Like you say in there, music can't be perfect, but we're constantly striving for this perfection historically in our art forms, with the exception of like people who are at the point in the cycle where they're breaking things because you can't be perfect. And I'm just wondering, you know, about the difference between proof and perfection, and kind of the elusive original. And if you could, I mean, you're sitting in front of me and I'm trying to figure this out, and I would love for you to tell me your thoughts.
Yes, there there is this wonderful kind of image that Plato came up with of us sitting in the cave, and what we see in the physical world around us are just the shadows of these kind of pure abstract structures and objects in the kind of like abstract mathematical realm, and that we are sort of tied and just seeing the shadows of these things. And I think for me, that is a very strong image, and I think kind of plays to my impression of of our universe, because as you say, the universe is kind of a poor approximation of the my pure mathematical world. I mean, let's take one of the structures, the blueprints that I talk about very early on in the book, which is the circle. The circle is obviously an incredibly fundamental, it's almost like uh, the building block of geometry. And we see the circles have been important for us as a species, really since we evolved. We see circles everywhere. We see the circle of the moon when it's full, the sun, the circle of when we throw a stone in water and we see the ripples, or even our eye, our soul, looking into our soul through the eye, it is a circle. But actually, and then you see we start creating circles. So some of the very first structures that humans made, the first art forms are like stone circles. 5,000, even longer years ago, we have Stonehenge, or these circles in Avebury. We are sort of representing this fundamental structure, and it's sort of also connected to abstractly to the idea of time as well. We understand time through circular behavior, with the sun coming up again and again. But the question is there really a genuine circle anywhere in the universe? Because clearly the stone circles are just approximations. The moon is a bit bumpy, so that isn't a circle. The iris is probably, and you see that's an interesting tension, because now quantum physics says that actually we believe that space and structures are essentially pixelated, that if you get down to a small enough scale, that everything comes in bits. So just in like an image, if you take an image which is a digital image and zoom in on it, at some point you find pixels and everything's made out of these very small things. So something can look quite continuous, but when you sort of zoom in on it, it's actually made out of little bits. And in if that's the case, then you can never make a perfect circle because it will always, at some point, you will zoom in on it and it will just look more like a thing with little edges around it. So I think that's an interesting tension because for me, mathematically, I can define and play around and talk about the circumference of a circle, measuring it in its pi. This is a number which starts 3.14159 and then goes off to infinity. But I can never actually write that number down physically because we are finite and the universe that we live in is the around us is finite. And so there's this incredible tension between what I can explore mathematically and what we can explore physically. But what's interesting again is then if you come to the arts, which actually Plato was very dismissive of the arts. He said, mathematics is the perfect thing. Then we see approximations of it in nature. And then the worst thing is this approximation that art does, which is, a poor version of nature, which is a poor version of mathematics. But I think actually that's a bit unfair because the wonderful thing about the world of the creative arts is that you can imagine things which don't have a physical reality. And so you can start to make, there's room there to move back to maybe things which are more perfect than could ever exist in the real world.
So when we're exploring things that are more perfect than could exist in the real world, how does that affect our understanding of the real world? Or is that like, how does that blueprint exist in that? If it cannot exist in our real,
Yeah.
how is that a translation of the blueprint if the blueprint itself is not perfection?
Yeah, you see, one of my theses that I propose in a couple of my books is that, why do we see so much mathematics in the universe around us? It is it every time we do some sort of investigation, it seems to be come down to an amazing bit of maths, which seems to make everything work. The fundamental particles which make up our universe seem to be described, and we seem to be able to discover new ones by following our mathematical nose. So one of my proposals is, the mathematics, going back to Plato, that the mathematics kind of exists and doesn't need a moment of creation. And what we are living in is a physicalized piece of mathematics. And by that physicalization, often maybe it can't be genuinely realized, but that's why these perfect structures turn out to be very, if we are a physicalized piece of mathematics, then understanding the maths is going to tell us how this universe works, even if it's actually just a kind of an approximation of those structures. So, and I think, one of the lovely things as well is, perfection is great, but actually, sometimes, I see this often in the way that artists will use a structure. They enjoy using something to perhaps begin the journey, but then the breaking of that structure is often as exciting and as thrilling as just following the rules themselves. So one of the examples I talk about in the book is Bach, whose music is incredibly structured and highly mathematical, but he won't be bound by those rules, and he enjoys those moments when he breaks the rules. So, for example, the Goldberg variations, this beautiful piece which starts off with this aria, then goes into 30 variations, ends with the aria. Already you're seeing that circle structure again, and actually halfway through the piece, he calls the variation, the 16th variation, an overture, which seems to say, well, okay, where is the beginning and end of this thing? But although there's a huge amount of structure, the canons explore mathematically, very interesting, but the last variation breaks the thing completely. It's called a quadlibet, a musical joke. It's just based on two folk tunes of the day. Seems to have nothing to do with the rest of the piece. But I think what Bach is saying is, you thought you knew what was going to happen. And that's because I've used all this lovely structure to get you to that point. But almost a bit like the Shakespeare, the Shakespeare used 11 to disrupt things and reveal how much structure there is before by disrupting it. And actually, a beautiful example of this is when I can't remember whether I put it in this book, but I certainly put it in another book that I went to visit a professor that I work with in Japan, and he
Not
took me up to right, okay. He took me up to Nikko, which is kind of like the Alhambra of Japan, these beautiful Shinto shrines and Buddhist temples, which have a lot of amazing patterns in the designs. But we went up through this arch, and it has 8 columns, which have this beautiful pattern, mathematical pattern running up them. 7 of them are the same, but the 8th one is upside down. And I said, oh, wow, the architect must have been so angry with the builders when they got this the wrong way round. And the professor I was working with said, no, this is a very deliberate act. They enjoying setting up this expectation and then breaking it by turning it upside down. And I think that's, you see that in the Arabic carpets, for example. They don't want to aspire to being God, who is the one who can realize perfection, and so they put a little bit of imperfection, but also that imperfection is only noticeable because there's so much structure elsewhere. If it was completely unstructured, it wouldn't be meaningful. So I love that way that artists will use structure, but then will enjoy breaking it almost to show you how much structure there has been.
Thank you for taking me here, because also as I'm taking notes, listening, and so much of my study is definitely not mathematics, but is how we understand the world through different story. But the trickster, it's the in mythology and everything else, the trickster is always like the core, and that's the trickster. That's the function of the trickster in geometry, which is like such a core part of so many different ways of understanding. Well, okay, we have 3 minutes for those of you who are listening live. If you would like to enter a question in the chat, since you showed up to join us in this moment in time, which I appreciate. If not, I have literally 9 more pages of questions, which I will not engage
Yeah,
with.
well, I was interesting because you said you don't do things the things you were interested in, you said not mathematics, but I suppose the point of this book is almost that a lot of the
It
things you
is
do in
mathematics.
life, like listening to music, you don't think of maths. And I suppose one of the messages of the book is I wanted people to kind of go away, oh, I didn't realize that was maths. And that maths is underpinning, the visual world, the architectural world, the music you love, the poetry that you're interested in, and sort of in a way, you're absolutely right. I wanted this book is sort of paying back that mathematician who wrote a book about what it means to be a mathematician and how creative it is. I hope this might be a book that a teacher will recommend to somebody who perhaps isn't thinking they're mathematically minded, but then actually discovers no, in here is a whole kind of like cabinet of wonder of ideas that will help you in whatever you do in your creative life.
Well, I feel like that is a beautiful circular beginning to end of our conversation. Even though but since we're the trickster and we have two more minutes, you mentioned that you were talking about Messi. I'm not pronouncing him, but he did the quartet at the end of time. Um,
Messiaen.
yeah, Messiaen, and how he was exploring the Fibonacci numbers. And you're talking about how an Indian, and now I'm quoting you, an Indian friend translated, allowing him to understand not only the rhythmic rules, but also the cosmic and religious symbolism that is contained in each decitala. And I know we literally have 1 minute, but are you telling me that each beat combination, and I went down a beautiful rabbit hole. It's a joy to read this book in the age of the internet. But that each beat combination is collectively a language for meaning, or each beat pattern is representative of a story. Is that what you're
Yes, I think it's a bit like words are our access to meaning, but music creates its own internal meaning, very often connected to our emotional world. And so a lot of those rhythms, which Messiaen was fascinated coming out of India, which actually, as you say, Fibonacci was about long and short, but Messiaen got interested in long, short, and something in between, and that gets even richer, and it starts to almost have its own language to it, and feelings like sometimes things can be abrupt and disruptive, or they might have a beautiful kind of fractal quality to them. So I think absolutely right. That we build up kind of this world of connection, and I think the point is, that these are just rhythms, but they're not just rhythms because they're something mathematical, but they're also something spiritual. They're also something linguistic, and this, you started off with that idea of translation, and this is, what I hope the book is aspiring to do, which is rather than us staying in all of our silos, to realize that there's so much kind of interplay flowing between the world of mathematics, music, architecture, which often is called frozen music, literature, the visual world. They're so interconnected in a way that often our education system doesn't celebrate well enough.
Well, thank you so much. I look forward to taking all of the nuggets here and going on to explore, how the musical math of programming emotion, which is like where where I want to keep chatting. But thank you again for taking the time. Thank you all for being here in this moment, also in the future, and really for not only buying Blueprints from the Country Bookshop, but reading it, because it's a treat. So thank you so much.
Thank you for inviting me to the bookshop.
There you go. Bye.